they became the people who travelled the farthest in history. This was the absolute pinnacle of human engineering. But this perfect victory was actually hiding a horrifying list of failures. Even the best was not good enough. Because the story behind that seemingly perfect splashdown is not a bright one. 4 astronauts returned in a heat shield that was known to have developed over 100 cracks on a previous mission and was never fully repaired. Because of this, they absorbed 18% more radiation during their journey than even the worst-case scenario model predicted. But that's not the most shocking part. This fact aligns disturbingly with the mysterious heart diseases that are killing Apollo astronauts at a rate 4 to 5 times higher. If you too care about the engineering reality beyond the official statements, like and subscribe. Because your beliefs are about to be shaken, are you ready? Let's begin. We thought the future of humanity in space was bright. Flawless missions, broken records, triumphs that made the headlines. The Artemis II mission was presented in exactly this way. A perfect landing, a historic achievement, the declaration that the path to the lunar surface was officially open. But now we know that beneath this brilliant picture lies a much more complex, much more alarming reality. Because the moments of victory shown by the cameras were merely a curtain, hiding just how dangerous this 10-day journey truly was and what awaits us in the future. This is why everything began with that seemingly perfect landing on April 10th, 2026. The spacecraft named Integrity touched down in the Pacific Ocean just 40 meters off the coast of California. It floated down beneath 3 massive red and white parachutes. It covered the final meters at a speed of about 32 kilometers per hour. It made contact so close to the target coordinates that recovery teams measured the error at less than 1 mile. NASA called it a bullseye, because gases, by every measurable standard they used, that's exactly what it was. This was an incredible feat of engineering. Imagine, you launch a ball from Los Angeles, it strikes a coin in New York City, and you miss the target by less than the width of that coin. That was precisely the accuracy NASA achieved with an approximately 12,000 kilogram capsule, while it was travelling through the atmosphere at 32 times the speed of sound. That's why the 4 astronauts inside the capsule were greeted with applause and camera flashes when they stepped onto the deck. Because something truly historic had been accomplished. But these 4 people had accomplished much more than just a precision landing. They had broken a record that hadn't been broken for 53 years. They surpassed the distance reached by the Apollo 13 crew in 1970, a distance no human had exceeded since. At the farthest point of their journey, on April 6th, they were exactly 406,771 kilometers from Earth. That is more than 6,400 kilometers farther than Apollo 13's record. The farthest humanity has ever traveled from the planet that created it. This achievement wasn't just about numbers. Because Victor Glover became the first black astronaut to fly beyond low Earth orbit. Christina Koch, who already held the record for the longest single spaceflight by a woman at 328 days, added the title of farthest woman from Earth. Jeremy Hansen became the first Canadian to make this journey, and Commander Reed Wiseman led this historic team. The applause wasn't just for a landing, the applause was for crossing a boundary that had stood for half a century. But what's truly interesting is that on the day this record was broken, they witnessed something no one in human history had ever seen before. Because that day, they watched a solar eclipse from behind the moon. For a full 53 minutes, the Earth blocked the sun. As the crew floated over the dark side of the moon, they watched the sun's corona extend outward from the eclipse disk. In the words of astronaut Jeremy Hansen, these streamers of plasma were like baby hair. Christina Koch photographed the topography of the lunar limb in front of the corona, producing images that planetary scientists will study for years. It was the kind of beautiful, unprecedented moment that justifies the entire endeavour of human spaceflight. But, on that very same day, during this moment of unique beauty, something else happened that was less photogenic, but perhaps far more important. The crew observed 5 to 6 flashes of light on the dark lunar surface. These were meteorite impacts, pieces of space rock hitting the moon at speeds up to 70 kilometers per hour. and they watched it happen from orbit to you in real time. Victor Glover reported one near the South Pole, close to where the future base camp is planned. These impacts were part of the brutal reality behind the magnificent images and broken records. They were living proof of how hostile the lunar environment truly is. This is why moments like that perfect landing, the broken distance records, and the unique solar eclipse images make the news. They are the things that get carried in the headlines, the things NASA's Public Relations Office is designed to magnify. And they should be magnified because they are real and they are remarkable. But that is not the whole story. It's not even the most important part of the story. The most important part is the part you have to look for. The part that emerges not in press conferences, but in post-flight inspection reports, engineering change requests, and independent safety panel reviews. It's the part that doesn't get a standing ovation. I am here to tell you, there is a second story lying beneath the first one, and it's a story that almost no one is telling, because if you look carefully at what really happened during those 10 days, if you look at the corporate patterns shaping every choice NASA made, at the data that came back, you start to see something that the celebrations were not designed to show you. You start to see a gap. The gap between what we say and what we can do, the gap between our ambitions and our engineering, the gap between the press conference and the post-flight inspection report. And this gap, this distance between the story we tell and the reality underneath, is not new. It has emerged before in the history of human spaceflight, and the last 2 times it emerged, people died. Because just beneath that flawless picture that made the headlines, cracks were hiding, and those cracks were, quite literally, on the surface. These cracks were in the heat shield of the Orion spacecraft. The shield is made of a material called avcoat. It's an ablative thermal protection system. This means it's designed to absorb the heat of re-entry by slowly burning away, charring, melting, and vaporizing layer by layer. Think of it like an ice cube in a drink, absorbing heat. The ice disappears, but the drink stays cold. Avcoat is the ice cube between the crew and the approximately 2,760 degrees Celsius superheated plasma that forms around a spacecraft as it re-enters Earth's atmosphere at Mach 32. The theory is elegant, but the reality turned out to be far more complicated, because in November 2022, when NASA flew the uncrewed Artemis I mission around the Moon and brought the Orion capsule back through the atmosphere, something went wrong with the avcoat. Not catastrophically wrong, not mission-endingly wrong, but wrong enough to halt the entire program for months. Everything stopped, while engineers tried to figure out what happened, because you have to understand what re-entry means. Within seconds, Orion is enveloped in a sheath of ionized plasma, essentially a fireball. The external temperatures are high enough to melt steel, titanium, and almost anything else humans know how to make. Inside that fireball, the crew relies on one single thing for their survival, that the avcoat heat shield between them is doing its job. That is why what they found when they pulled the Artemis I capsule out of the Pacific was so shocking. There were over 100 points of damage on the shield's surface. The avcoat material had not melted away smoothly as designed. Instead, it had cracked. Pieces of charred material had broken off in fragments, leaving divots and pits in the shield's surface. But this is where the story gets truly interesting, because, after months of testing and analysis, NASA identified the root cause. The problem was gas. During the skip re-entry trajectory that Artemis I flew, gases became trapped inside the material. The outer char layer was not porous enough to let them escape. Pressure built up, the char cracked, pieces broke away. A heat shield is not optional. Without it, the heat of re-entry reaches the spacecraft's aluminum alloy structure. Then, and what happens next, is what happened to the Space Shuttle Columbia. The vehicle breaks apart. The crew does not survive. The heat shield either works, or it doesn't. That is why NASA's solution to this problem was a piece of engineering that should both impress you with its cleverness and make you a little uneasy at the same time. Because NASA didn't redesign the material, they didn't replace the heat shield on the Artemis II capsule with a new material. What they did instead was change the trajectory. The re-entry profile for Artemis II was changed from a skip re-entry to what engineers call a lifting re-entry. The idea is counterintuitive. By keeping the heating rate higher and more consistent, They ensured the outer char layer would stay hot enough to remain porous. The gases could escape. The pressure didn't build up. The cracking didn't occur. Read that again. NASA's solution to a heat shield that cracked under too much heat at one stage of re-entry was to expose the crew to more heat, not less. They didn't fix the material. They changed how they flew through the atmosphere to work around it. Because the new trajectory created the heating conditions that prevented a flawed material from failing. This engineering gamble seems to have paid off. The capsule landed, the crew survived, the celebration happened. But the inspection is still ongoing, and this is not the only unsettling element in the story. Because the heat shield wasn't the only thing that didn't work as planned. There was a cascade of small failures. The Orion spacecraft has a toilet that cost about $30 million to develop. But that toilet broke on day one of the mission, the waste management system malfunctioned, and the crew had to work with mission control in Houston to troubleshoot the problem. The $30 million system failed on its first crewed flight, on the first day, and required a manual fix. Shortly after launch, the crew experienced a loss of communication with mission control. For a period of time, the most advanced crewed spacecraft ever built was flying toward the moon on a one-way phone line. And on top of it all, NASA confirmed after landing that the service module would require a valve redesign. This indicates something in a system responsible for keeping the crew alive worked outside of expectations. Each problem was manageable on its own, and they were managed. But when you look at all of them together, you have to ask a question that the celebrations don't invite. If this is the failure rate for a 10-day mission, what is it for a 30-day mission, a 90-day mission, or for a Mars journey that will take about 900 days? None of those missions will have a safety net that Artemis II had, the free return trajectory. This trajectory is designed so that even if every propulsion system on the spacecraft failed completely, the moon's gravity would automatically send the capsule back to Earth. This is what saved the lives of the Apollo 13 crew. But that safety net only applies to missions that loop around the moon and come back, not for missions that will land on the surface, not for missions that will go to Mars. The anomalies on Artemis II were manageable because the mission architecture was forgiving. The next missions will not be. But beyond all these mechanical glitches and engineering gambles, there was something else, invisible, that the crew brought back with them in their bodies, a threat that could be measured but not seen. Because the heat shield can protect you from the plasma fire, but now come the truly shocking numbers, the number that almost no one mentioned during the celebrations, the fact hidden deep in the data stream, 12 millisieverts. That was the preliminary result for the radiation dose that each of the 4 Artemis II crew members was exposed to during their 10-day journey. That number alone was not a crisis. It was within NASA's career safety limits. But what makes this number interesting is that it was about 18% higher than what NASA's pre-flight models had predicted. This was not a rounding error. It was not a calibration issue. A full 18%, almost 1/5 higher than every model, every simulation, every calculation produced by NASA's radiation environment team that had been preparing for this mission for years. This was not supposed to happen. Our models were not supposed to be that wrong. Because an 18% error on a 10-day mission makes for an acceptable difference. But if you take that same 18% error and apply it to a longer mission, the situation changes. Apply it to the Artemis IV mission, where astronauts will spend weeks on the lunar surface without the protection of Earth's magnetic field. Or to a Mars mission that will last about 900 days. There, an 18% error means the difference between staying within NASA's career dose limit of 600 millisieverts and exceeding it. It is the difference between an acceptable lifetime increase in cancer risk and an unacceptable one. Because this radiation is not like a medical X-ray. These are galactic cosmic rays. They are atomic nuclei accelerated to near the speed of light by the shockwaves of supernovas that exploded millions of years ago. A single heavy ion cosmic ray, an iron nucleus moving at 90% the speed of light, can damage a chain of cells as it passes through a human body, severing DNA strands. That's why this 18% deviation wasn't just a number. It was a warning that our understanding of the deep space radiation environment was not as complete as we thought. But this 18% error doesn't mean much on its own. The truly terrifying picture emerges when it is combined with 50 years of data. Data that comes from the only other people who have done what the Artemis II crew did, the Apollo astronauts. Because, in 2016, a researcher from Florida State University named Michael Delp published a study. Delp divided all NASA astronauts into 3 groups: those who had never flown, those who had only flown in low Earth orbit, and the 24 Apollo astronauts who went to deep space, to the Moon. The results were shocking. 11% of the low-orbit astronauts had died from cardiovascular disease. But, for the Apollo lunar astronauts, that rate was 43%, 4 to 5 times higher than the other groups. This seemed impossible. These were the healthiest people on the planet. They were expected to have a lower risk of dying from heart disease. The only difference between them was their exposure to deep space radiation. Delp's theory was that galactic cosmic rays were causing molecular-level damage to the cells lining the inside of their blood vessels. This damage accumulated over decades, leading to heart attacks and strokes at much higher rates than expected. The 18% deviation brought back by Artemis II revived this 50-year-old, terrifying data. Because it meant that deep space travel could have a hidden, lethal cost that only emerges decades later. And now comes the real shockwave. Because the danger wasn't just coming from the outside. The capsule itself was a ticking time bomb. So many systems were not expected to fail on a 10-day mission. The $30 million toilet on the Orion spacecraft broke on the first day of the mission. Shortly after launch, communication with mission control was lost. The astronauts could hear Houston, but Houston could not hear them. They were heading to the Moon on a one-way phone line. And most importantly, NASA confirmed after landing that a valve in the European service module would need to be redesigned. This was a critical system responsible for keeping the crew alive, and it had not performed as expected. Each was a manageable problem on its own. But a failure rate of this intensity should not be seen on such a short and forgiving mission. Artemis II had a safety net called a free return trajectory. This meant that even if everything failed, the Moon's gravity would bring them home. But future missions will not have this net. So, the real question is, if this is the failure rate on a 10-day mission, what will the failure rate be on a 900-day Mars mission? A system that is 99% reliable means it has a 90% chance of working flawlessly for 10 days. But that same 99% system has only a 36% chance of working flawlessly for 100 days. Artemis II showed us what the baseline failure rate of this spacecraft looks like, and that rate was not 0. It was not even close to 0. These findings are alarming even individually. There is an 18% error in our radiation models. There is an unexplained anomaly in the death rates of Apollo astronauts, and there is a worrying number of system failures on a brand new Statistics multi-billion-dollar spacecraft. But, when they come together, they raise a much darker question. Was this just bad luck? Or was the most dangerous and least talked about pattern in human spaceflight a pattern that has twice before ended in disaster for NASA? Back. Because that insidious process that destroyed Challenger and Columbia, and that insidious process, is not just a memory from the past. Because it seems to be reviving right now, at the heart of the Artemis program, and the biggest proof of it came with a quiet change that no one was talking about loudly. And while Artemis II was flying around the Moon, while everyone was celebrating, the most important date in the program was quietly changed. The Moon landing mission was cancelled, at least not as planned. This should not have happened. But it did, and this was just one of the most shocking parts of the story. Because, on February 27th, 2026, just a month before the launch, the NASA administrator confirmed a revised plan for the next missions, Artemis III. It was originally planned as the mission that would return American astronauts to the lunar surface for the first time since 1972. But it would no longer attempt a landing. Instead, Artemis III, targeted for mid-2027, was downgraded to an orbital test, not even in lunar orbit, in Earth orbit. The actual crewed lunar landing was now postponed to Artemis IV, targeted for early 2028. If that date holds, we will have set foot on the Moon exactly 56 years after the landing of Apollo 17 in December 1972, more than half a century, just weeks after the press conference where NASA said the path to the surface is now open. It turned out that the path was actually closed, and it was unclear when it would open. This is something that should not happen in a multi-billion-dollar program, but why? Why this sudden step back? Because we didn't have a vehicle to land on the moon. At least, we didn't have a ready one. The vehicle NASA was relying on for the success of this mission is called Starship, SpaceX's human landing system. By every measure, the most ambitious rocket ever designed, approximately 122 meters tall, designed to be fully reusable, and it uses a propulsion system that requires in-orbit refueling. This means launching between 10 and 16 additional Starship tanker flights, rendezvousing with the main vehicle in orbit, and transferring cryogenic fuel from one vehicle to another. This process has never been demonstrated on this scale before, and as of March 2026, Starship had not even completed this most basic fuel transfer demonstration. It had not passed its design certification review. NASA's own Aerospace Safety Advisory Panel expressed serious doubts about whether the timeline was achievable. The key technology required to take people to the moon had become the biggest risk factor for the entire program. This should not have happened. This was a terrible sign of just how fundamentally fragile the architecture was. And now for the truly frightening part. While we wait, others are not standing still, and not just our competitors. Our own infrastructure was collapsing. Just 4 months after this recording, in August 2026, China plans to land Chang'e 7 on the moon's south pole, not to orbit, to the surface. The mission's goal is to search for water ice in the same regions targeted by the Artemis program. They will be followed by Chang'e 8 in 2028, and together they will form the foundation of a robotic research station that they plan to establish a permanent base by 2035. But an even more urgent clock is ticking: the International Space Station, ISS. Humanity's only permanent outpost in space. It is targeted to be deorbited in January 2031, meaning it will be destroyed in less than 7 years. NASA's own Office of the Inspector General says it is unlikely that commercial space stations will be operational before this date. This means a gap that will likely last for years, where humanity has no permanent presence in orbit. This seemed impossible. How could a species celebrating its return to the moon be at risk of losing its only home in orbit? All these discoveries, the 18% radiation error, the 43% cardiovascular death rate mystery, the critical system failures, a postponed moon landing, and a collapsing orbital infrastructure, point to one disturbing conclusion. These are not independent incidents of bad luck. They are symptoms of a pattern. But how can so many things go wrong in so many different areas at the same time? How can so many warning signs be overlooked, or worse, ignored? Because this is not a coincidence. This is the operation of a process we have seen before in the history of human spaceflight. A process with specific rules, specific steps, and even a specific name. And to understand how this process works, we need to delve into its technical details, its psychology, and its darkest consequences. Because that insidious mechanism behind the Challenger and Columbia disasters is not just a sociology theory, it is also an engineering reality. So how exactly does this process, this thing called normalization of deviance, work? What is the mechanism behind this step-by-step process that makes danger invisible? Let's slow the tempo now and get into the technicals. Because understanding this concept is the key to understanding why the success of Artemis II might be more of a warning sign than a victory. This is the story of how large, complex organizations drift from safety to disaster. The person who first described this process was sociologist Diane Vaughan. While investigating the 1986 Space Shuttle Challenger disaster, Vaughan discovered that the accident was not the result of a single bad decision or a faulty O-ring. It was the result of a process that had developed over years. Vaughan called it the normalization of deviance. The idea is actually quite simple. Think of it like a creaking floorboard in your house. The first time you hear it, you say, oh, there's a problem, you call a repairman, or at least you worry. Yeah, but if nothing happens, if the creak continues, over time you start to ignore it. It's no longer a warning sign, it's just the sound the house makes. The anomaly has been normalized. Vaughan found that this is exactly what happened at NASA. A system is designed with certain specifications. On the first mission, something deviates from that specification. It's not catastrophic, but it is a measurable deviation. Engineers discuss it. Management assesses the risk. But because the mission was a success, because no one died, the deviation is accepted. This becomes the new normal. On the next mission, the same deviation occurs again. This time, it's expected. It's no longer an anomaly. It's just the way the system works. And over time, through repetition and survival, what was initially a deviation from design becomes normal. This process lay at the very heart of the Challenger disaster. Because the deviation on Challenger was O-ring erosion in the solid rocket boosters. NASA knew about this. It was not a secret. Engineers at Morton Thiokol, the company that manufactured the solid rocket boosters, had documented O-ring erosion on flight after flight. They had voiced their concerns. They had written reports. But the shuttles kept flying. A full 24 missions were launched with known O-ring erosion before Challenger. 24 times, the O-rings eroded and the shuttle survived. Each survival reinforced the belief that the erosion was within acceptable limits. Each safe return made it a little bit easier to approve the next launch. The risk had been normalized. The deviation had become the standard. On January 28, 1986, the 25th shuttle launch with known O-ring erosion encountered temperatures that pushed the erosion past an invisible line. It lasted only 73 seconds. 7 people died. Millions watched it live. Vaughan's work shifted the blame from individual bad actors to systemic organizational behavior. The problem wasn't that NASA managers were reckless. The problem was that they were embedded in a system that made each individual decision seem reasonable, until the cumulative trajectory pointed toward disaster. But an even more insidious mechanism was at work within this process. It was the reversal of the burden of proof. On the morning of January 28, 1986, the temperature at Kennedy Space Center in Florida was only 2 degrees Celsius. Icicles had formed on the launch pad the night before. Morton Thiokol engineers had argued against the launch in a teleconference with NASA the previous evening. They had data showing that the O-ring seals lost their flexibility in cold weather. They had a chart. They had test results. But NASA pushed back. The agency was under schedule pressure. And in that conversation that night, one of the most crucial moments in the entire Challenger story occurred. NASA managers asked Thiokol to prove that it was unsafe to launch, whereas normally, NASA had to prove that it was safe to launch. This reversal, this shift in the burden of proof from prove it's safe to fly to prove it's unsafe to fly, was the moment when the normalization of deviance went from being a corporate habit to an active guest's conscious acceptance of risk. Thiokol management overruled their own engineers. The launch was approved. 73 seconds later, the O-ring failed. Hot gas breached the external tank. The shuttle broke apart at an altitude of 14,600 meters. The crew cabin separated and fell for 2 minutes and 45 seconds before impacting the Atlantic Ocean at a speed of about 320 kilometers per hour. At least some of the crew members were conscious during the fall. Their emergency air packs had been activated. Because, for almost 3 minutes, they were alive, aware, and falling, and there was nothing anyone could do. This is why the people who die when risk is normalized are not abstractions. They are people who trusted that the organizations responsible for their safety were making decisions based on evidence, not momentum. And then, exactly 17 years later, on February 1st, 2003, the process repeated. The Space Shuttle Columbia disintegrated during re-entry over Texas and Louisiana. This time, the cause was a piece of foam insulation that struck the leading edge of the shuttle's left wing during launch. This impact damaged the reinforced carbon-carbon thermal protection panels. When Columbia re-entered the atmosphere 16 days later, superheated plasma entered the wing structure through this breach, and the orbiter was destroyed. 7 more people died. This carries an even more direct parallel to the Artemis heat shield situation. Because the foam shedding was not a surprise, it was expected. It had been happening for years, for decades. In fact, Over the course of 113 shuttle missions, foam had repeatedly separated from the external tank during launch. The damage it caused had been observed, documented, analysed, and accepted. Because foam had shed for 113 missions and no one had died because of it, the deviation had been normalised. The risk had been accepted. Diane Vaughan was invited to serve on the Columbia Accident Investigation Board, and when she examined the organisational dynamics that led to the disaster, she found the same pattern she had documented with Challenger 17 years earlier. The same gradual acceptance, the same organisational drift. She saw how an organisation that knew it had a problem, that had the documents, the analysis, the warnings of the problem, slowly redefined the problem from an anomaly to a feature from an acceptable risk to normal. The mechanisms that destroyed Challenger and Columbia both revolved around thermal protection. Challenger's O-rings were a thermal seal. Columbia's panels were thermal protection. Both failures were about the boundary between survivable temperatures and lethal ones. And both failures occurred in systems where known deviations had been normalized over multiple flights. Now consider the Avcoat heat shield on the Orion spacecraft, the thermal protection system that cracked and spooled in over 100 places on Artemis I, the material that was not replaced for Artemis II, but instead was worked around by changing the re-entry trajectory. Challenger's O-ring survived 24 flights before it failed. Columbia's foam survived 113 missions. The Avcoat that cracked on Artemis I and was worked around instead of fixed has survived one crewed flight. All of these processes show how warning signs become background noise. But how exactly is this pattern re-emerging in the Artemis program? How does the heat shield decision fit this process one-to-one? And most importantly, is there any reason to think this time will be different? Because, when we get down to the story of the Avcoat heat shield and the way NASA fixed it, the parallels are not just disturbing, they are identical. This is why, to understand why the Artemis II heat shield could be a harbinger of disaster, we need to grasp exactly how this pattern works. Because this is not just a story about the past. This is a process actively at work in the decisions shaping the Artemis program right now. And one of the most critical elements of this process is what Vaughan called external pressure. Schedule pressure, budget pressure, political pressure, competition. Study these factors act as catalysts that accelerate the normalization of deviance. Just like a heat source speeds up a chemical reaction, these pressures push an organization away from safety and toward risk more quickly. Because the O-ring concerns on Challenger were overlooked in part due to launch schedule pressure. The foam concerns on Columbia were not fully investigated because of the operational tempo of the shuttle program. These pressures are the environmental factors in which every decision is made. And the Artemis program, as of April 2026, is operating under extraordinary external pressure. The congressional scrutiny over the program's cost, roughly $4.1 billion for each SLS and Orion launch, is growing. The geopolitical competition with China is real and accelerating. The Starship HLS delays are compressing the timeline, and the public expectation created by NASA's own messaging creates its own momentum. Each of these pressures pushes in the same direction. Fly, keep moving, maintain the schedule, don't slow down. The heat shield decision, the decision to fly the Avcoat workaround instead of redesigning the material, was made in exactly this pressure environment. I'm not saying this pressure caused the decision. But Vaughan's research shows with historical rigor that this kind of pressure accelerates exactly this kind of normalization of deviance. And here is where the most insidious part of the pattern kicks in: success. The fact that the mission was successful, that the crew survived, reinforces the pattern. Every single person in the chain of command who approved the Avcoat workaround now has data that suggests they were right. That data will make the next decision easier. It will make the next deviation a little more acceptable. It will make the next workaround a little less concerning. Let me put it in an analogy. Imagine you have a car and one day you notice the brake pads are wearing unevenly. The mechanic tells you the pads are not faulty, but they are wearing in a pattern the manufacturer did not design for. Instead of replacing the brakes, you decide to change the way you drive. You brake earlier, more slowly, and for a year, the brakes work fine. After a year, you slowly revert to your old driving habits. Because the brakes have been working fine for a year and changing your driving style is a hassle. This is the normalization of deviance in daily life. Now scale that up to a spacecraft entering the atmosphere at Mach 32 with 4 people inside, and you understand why this concept is so dangerous. But there is another technical mechanism within this pattern: structural secrecy. This means that the structure of an organization prevents critical information from reaching decision makers. This is not a deliberate cover-up. This is a problem with how information flows in large bureaucracies. On Challenger, the engineers' concerns about the O-rings were diluted as they moved up through layers of management. The decision makers at the top did not fully grasp the urgency and concern felt by the engineers at the bottom. On Columbia, engineers' requests for satellite imagery to assess the damage were rejected by management. The request could not travel up the organization. It's like the architecture of a building making it difficult to access certain rooms. Everyone can be well-intentioned, but the structure prevents information from flowing freely. NASA has taken great steps over the years to address this problem. But under the pressure of a $4.1 billion launch cost and a space race with China, it can still be difficult for bad news to flow upwards, especially if that news means slowing down a multi-billion-dollar program. All these mechanisms, normalization of deviance, external pressure, and structural secrecy, come together to create what some at NASA call the third chapter. After the Challenger and Columbia disasters, both accident investigation boards documented these organizational failures, and both hoped that NASA had learned these lessons and would never repeat them. But the data from Artemis II may indicate that this third chapter has begun. Artemis I revealed a significant unexpected anomaly in the Avcoat heat shield, over 100 char liberation events. NASA's own Office of Inspector General report identified 3 potential crew loss of life mechanisms resulting from this spalling. Despite this, NASA's response was not to redesign the material, but to change the trajectory. This is a solution. But it is also, in Vaughan's terminology, a deviation that is now accepted as the new normal. The mission was a success, and that success legitimizes the deviation. Challenger's O-ring survived 24 flights. Columbia's foam survived 113 missions. The Avcoat of Artemis II has survived 1 crewed flight. We're now in year 1 of Avcoat's normalization window. All of these technical and organizational mechanisms come together to create that gap between the story we tell and the reality underneath. The gap between triumphant press conferences and not yet published inspection reports. But the most exciting and perhaps most frightening part of this story is how all these theories, all these historical parallels, converge with concrete, measurable, and shocking results. Because what happened during the journey of Artemis II proved that these patterns are not just abstract sociological concepts, they were real-time, physical events that threatened human life. And now, it is time to look at the most critical moments of the journey, what went wrong in those moments, and what it means for our future. Because the climax starts now. And at that climax, there were not just broken systems, but also measurable, concrete, and terrifying. Because these patterns were not just abstract sociology theories, they were real-time, physical events that threatened human life during the 10-day journey of Artemis II. And now, we're pushing the tempo to the maximum. We are reaching the climax. This is the story the celebrations concealed. This is the truth the headlines did not tell. This is the real message Artemis II brought home. Get ready. Because we are now coming to the moment where it all comes together. The first shockwave was silent. It was insidious. But it was the first sign of just how fragile the system was. It wasn't one failure, it was a series of failures. A cascade of failures pouring down a $30 million toilet. It broke on day 1, a crew of 4, a 10-day mission. And their waste management systems were not working. One of the crew members had to take on a role described in NASA's own blog post as space plumber. But that was only the beginning. Shortly after launch, communication was lost. Completely. Mission Control could not hear the most advanced spacecraft ever built as it headed to the moon. The astronauts could hear Houston. But Houston could not hear them. It was an asymmetrical failure, a one-way phone line. Commander Reed Wiseman's Microsoft Outlook email accounts weren't working. This might sound comically mundane. But 320,000 kilometers from Earth, NASA had to remotely access the computers on the ground to solve the problem, and the worst of it. NASA confirmed after landing that the service module would require a valve redesign. This was the power and life support backbone responsible for keeping the crew alive, and it had not performed as expected. Each was a manageable problem on its own. But a failure rate this dense should not have happened. This is something that should not happen on a brand new, multi-billion-dollar spacecraft. These were not small bugs found on a test flight. This was an alarm bell showing how fundamentally stressed the system was. Because these failures occurred on a forgiving mission. But the next missions would not be forgiving. But these small failures were nothing compared to the real nightmare. The heat shield, that critical piece at the heart of everything. When Artemis I returned in November 2022, the engineers were horrified. The shield was not intact. It had cracked. It was shattered in over 100 places. The avcoat material had not melted smoothly as designed. Charred pieces of material had broken off in fragments. It left divots and pits in the surface. In some places, the char layer had peeled off in such large sections that it had created a visible trail of debris behind the spacecraft during re-entry. This should not have happened. This was impossible. This material had worked on Apollo. But now, its modern version was failing its most basic task. It was the only thing standing between the crew and a 2,760 degrees Celsius plasma fireball, and that one thing was falling apart. NASA's own Office of Inspector General report identified 3 potential crew loss-of-life mechanisms from this spalling. This included the possibility that heat could reach and melt the structural bolts holding the heat shield assembly together. This was not just cosmetic damage. This could have been a repeat of the Columbia disaster. This was a potential death warrant, and this reality cast a shadow over the entire program. Because they were going to use the same heat shield for the next crewed mission. And then the most incredible thing happened. The decision that pushes the limits of human reason. NASA didn't fix the material. They didn't change the heat shield. Instead, they changed the orbit. They flew into more heat. Yes, you heard that right. Their solution was to expose the crew to more heat, not less. This was a gamble unprecedented in the history of engineering. The idea was completely counterintuitive. They designed a new profile called a lifting re-entry. This profile kept the heating rate higher and more consistent, ensuring the outer char layer stayed hot enough to allow gases to escape. So, pressure didn't build up, cracking didn't happen. This was a perfect example of the normalization of deviance. Instead of fixing the root cause, the faulty material, they changed the environment to work around the flaw. This was like trying to fix a leaky roof by just hoping it doesn't rain. And this massive gamble was played on April 10th, 2026 with 4 people inside, and it worked. The capsule landed, the crew was alive. But this success sowed the seeds of disaster, because it normalized the deviation. It made it even easier to fly the next mission saying, "This method works." Just like Challenger's O-rings worked 24 times. Until they didn't on the 25th time, Artemis had just taken the first step in this horrifying cycle. But the heat shield can protect you from fire. What protects you from the cosmos itself? And now, we come to the most insidious, most invisible, and perhaps the most lethal climax of the entire story. 12 millisieverts. The radiation dose the Artemis II crew was exposed to in 10 days. That number was a lie, at least an incomplete lie. Because that figure was a full 18% higher than what all of NASA's pre-flight models had predicted, almost 1/5 more. This was not a rounding error. This was proof that our models, our best guesses about the radiation environment in deep space, were seriously flawed. This should not have happened. On a 10-day mission, this 18% difference is acceptable. But when you apply it to a 900-day Mars mission, this error means the difference between an acceptable cancer risk and a fatal dose. It could be the difference between astronauts returning home healthy and developing cancer in their 40s or 50s, and this radiation is unlike anything we know. These are galactic cosmic rays, atomic nuclei accelerated by supernovas that exploded millions of years ago. A single iron nucleus can tear through a chain of cells as it passes through your body. It can sever your DNA. And what Artemis II showed is that our ability to predict this invisible bombardment was 18% worse than we thought. This, even on its own, was a terrifying discovery. And now, the ultimate apocalypse, the most horrifying number in the entire story, the number hidden in plain sight for 50 years, the truth never mentioned in any press conference, 43%. That shocking study published by Michael Delp in 2016. The study examined the 24 Apollo astronauts who went to the moon, and what he found shook the scientific world. The rate at which these 24 astronauts, the only humans to have ever gone beyond Earth's magnetic shield, died from cardiovascular disease was 43%. This was 4 to 5 times higher than the rate for astronauts who only stayed in low Earth orbit, 11%. This was impossible. This should not have happened. These men were the healthiest people on the planet. What was the only difference between them? Deep space radiation. Delp's theory was this. This radiation was slowly damaging the inner lining of their blood vessels over decades, creating a kind of time bomb. This damage was exploding as heart attacks and strokes in their 40s, 50s and 60s. Could the greatest triumph of the Apollo program also be its deadliest legacy? That 18% radiation surplus brought back by Artemis II revived this 50-year-old, terrifying ghost. Because it meant that the biological cost of deep space travel could emerge long after the mission is over, decades later. This was the biggest readiness gap of all. A gap in time, a decades-long delay between cause and effect. This meant we might be sending people into an environment that is slowly killing them, and we might not even realize it until it's too late to change. A broken spacecraft, a cracked heat shield, a miscalculated radiation dose, and a 50-year-old death warrant. These are not independent events. These are symptoms of the same fundamental problem, the massive chasm between our ambitions and our capabilities. But when all these hardware failures, these biological dangers, and this corporate blindness come together, an even bigger question arises. This isn't just about the Artemis program itself. This shows how fundamentally flawed the entire architecture of humanity in space is. Because, as we grapple with these problems, another critical piece of the system is collapsing before our very eyes, and the consequences of this collapse were unimaginable. This is why, when all these hardware failures, biological dangers, and corporate blindness come together, an even bigger question arises. This isn't just about the Artemis program itself. This shows how fundamentally flawed the entire architecture of humanity in space is, because as we grapple with these problems, another critical piece of the system is collapsing before our very eyes. And this collapse reveals the biggest and most devastating irony of the entire program. We had lost the ability to land on the moon. This was a moment unprecedented in history, and no one was aware. Because the real bomb drops now, quietly, not in a press conference, with a revision, February 27th, 2026, just a month before the launch. NASA confirmed that the Artemis III mission would no longer land on the moon. This was supposed to be the first lunar landing mission since Apollo 17, since 1972. But now, it was downgraded to an orbital test, in Earth orbit, not even lunar orbit, and the actual landing was now postponed to Artemis 4 at the earliest in 2028. This, if the date holds, would be 56 years after our last footstep on the moon. More than half a century. Just weeks after the press conference where NASA said, the path to the surface is open. It turned out the path was actually closed, and it was unknown when it would open. This should not have happened. This was impossible. Humanity had developed the ability to go to the moon for the second time in history, but then, at the very peak, it gave up on using that ability. How was this possible? This was like a country building a giant ship to cross the ocean, and then not allowing it to leave the port. Because, behind this decision, lay the biggest paradox of the entire Artemis program. Because, at the center of everything was a single name: Starship, SpaceX's human landing system. This was the vehicle NASA was relying on to land astronauts from lunar orbit to the surface and bring them back. And this vehicle was not ready. It was far from ready. This was the most ambitious rocket ever designed. approximately 122 meters tall, fully reusable. But its most critical feature was that it required in-orbit refueling. This meant launching between 10 and 16 separate Starship tanker flights, rendezvousing with the main vehicle, and transferring cryogenic fuel from one vehicle to another in zero gravity. This was a technology that had never been attempted on this scale before, and as of March 2026, Starship had not even completed this most basic demonstration. It had not passed its design certification. NASA's own safety auditing body stated it had serious doubts about whether the timeline was achievable. The vehicle that was supposed to take people to the moon was little more than a dream on paper, and because of this, the entire program came to a halt. This was the Achilles heel of the Artemis program. The most capable vehicle was also the least ready, and the schedule pressure was pushing the program to stick to dates that even its own safety experts did not believe in. But when all these hardware failures, these biological dangers, and this corporate blindness come together, an even bigger question arises. This isn't just about the Artemis program itself. This shows how fundamentally flawed the entire architecture of humanity in space is. Because, as we grapple with these problems, another critical piece of the system is collapsing before our very eyes, and the consequences of this collapse were unimaginable. This is why, when all these hardware failures, biological dangers, and corporate blindness come together, an even bigger question arises. This isn't just about the Artemis program itself. This shows how fundamentally flawed the entire architecture of humanity in space is, because as we grapple with these problems, another critical piece of the system is collapsing before our very eyes, and this collapse reveals the biggest and most devastating irony of the entire program. We had lost the ability to land on the moon. This was a moment unprecedented in history, and no one was aware. Because the real bomb drops now, quietly, not in a press conference, with a revision, February 27th, 2026, just a month before the launch. NASA confirmed that the Artemis III mission would no longer land on the moon. This was supposed to be the first lunar landing mission since Apollo 17, since 1972. But now, it was downgraded to an orbital test, in Earth orbit, not even lunar orbit, and the actual landing was now postponed to Artemis 4 at the earliest in 2028. This, if the date holds, would be 56 years after our last footstep on the moon, more than half a century, just weeks after the press conference where NASA said, "The path to the surface is open." It turned out the path was actually closed, and it was unknown when it would open. This should not have happened. This was impossible. Humanity had developed the ability to go to the moon for the second time in history, but then, at the very peak, it gave up on using that ability. How was this possible? This was like a country building a giant ship to cross the ocean, and then not allowing it to leave the port. Because, behind this decision, lay the biggest paradox of the entire Artemis program. Because, at the center of everything was a single name: Starship, SpaceX's human landing system. This was the vehicle NASA was relying on to land astronauts from lunar orbit to the surface and bring them back. And this vehicle was not ready. It was far from ready. This was the most ambitious rocket ever designed, approximately 122 meters tall, fully reusable. But its most critical feature was that it required in-orbit refueling. This meant launching between 10 and 16 separate Starship tanker flights, rendezvousing with the main vehicle, and transferring cryogenic fuel from one vehicle to another in zero gravity. This was a technology that had never been attempted on this scale before, and as of March 2026, Starship had not even completed this most basic demonstration. It had not passed its design certification. NASA's own safety auditing body stated it had serious doubts about whether the timeline was achievable. The vehicle that was supposed to take people to the moon was little more than a dream on paper, and because of this, the entire program came to a halt. This was the Achilles heel of the Artemis program. The most capable vehicle was also the least ready, and the schedule pressure was pushing the program to stick to dates that even its own safety experts did not believe in. But the most brutal irony of this story comes now. While we wait, others are not standing still, and not just our competitors. Our own infrastructure, our own home, was collapsing before our eyes. the International Space Station, ISS, humanity's only permanent outpost in orbit, inhabited continuously since the year 2000, and it is targeted to be deorbited in January 2031, meaning, in less than 7 years, it will be sent to the bottom of the ocean, and no one has a good answer to the question of what will replace it. NASA has contracted with several companies to develop commercial space stations. But NASA's own Office of the Inspector General stated that these stations are unlikely to be operational before the early 2030s. This meant a gap that would likely last for years, a period where humanity has no permanent presence in orbit. This seemed impossible. How could a species celebrating its return to the moon lose its only home in orbit? The station itself was aging, its cooling loops were leaking, its structural modules were showing signs of fatigue. That chain of continuous presence, which had lasted for 25 years, was about to be broken, and it seemed no one had a plan B. This was a moment unprecedented in history. Humanity had perfected the ability to reach space, but was about to lose the ability to stay in orbit. And all these failures, all these delays, and all this collapsing infrastructure illuminate one terrifying truth: the race, the quiet, relentless race with China. While we were postponing Artemis III, China was not stopping. Just 4 months after this recording, in August 2026, China plans to land Chang'e 7 on the Moon's south pole, to the surface. The mission's goal is to search for water ice in the same regions targeted by Artemis. They will be followed by Chang'e 8 in 2028, and together, they will form the foundation of a permanent robotic base that China and Russia plan to establish by 2035. Don't say this isn't a competition, that science knows no flags, because the timeline matters, and this pressure accelerates the process we call normalization of deviance in dangerous ways. If Artemis IV slips past 2028, which experts believe it could, then the possibility is very real that China will have an active robotic infrastructure at the South Pole before a single American astronaut sets foot on the lunar surface. This is not a failure of American engineering. This was a result of architectural choices made years ago for political and economic reasons. Choices that had little to do with the fastest or most efficient path. And the fact that each SLS launch costs $4.1 billion makes this race even more impossible. This is not a technical limitation. This is a financial shackle, and it means the pace of progress is determined not by how fast engineers can solve problems, but by how often Congress is willing to write a $4 billion check, a delayed landing, a collapsing space station, a rapidly advancing competitor, and a broken architecture underlying it all. This is the real picture that Artemis II brought home. The cold, hard truth hidden by the celebrations and headlines. The readiness gap is not closing, it is growing exponentially. Every new finding, every new delay, every new system failure adds a new variable to the equation. But, in the midst of all this chaos, all these failures and disappointments, it is time to stop and think, time to look beyond all these technical details, these geopolitical races, and these corporate mistakes. Because these numbers and these reports are not just telling us something about the state of our space program, they are telling us something deeper about ourselves, about our species, about the nature of our ambitions and our limits. So what does this mean for us? What is the real meaning behind all this effort, this risk, this enormous cost? Because, at the end of this journey, what awaits us is not just the lunar surface, but also, not just a lunar surface, but also a confrontation with fundamental questions about ourselves. And now, that moment has come. Now is the time to stop and think, time to look beyond all these technical details, these geopolitical races, and these corporate mistakes. Because these numbers and these reports are not just telling us something about the state of our space program, they are telling us something deeper about ourselves, about our species, about the nature of our ambitions and our limits. And now, we face that most important question. What is the real meaning behind all this effort, this risk, this enormous cost, in this cosmic ocean? Where exactly is our place? Because the journey of Artemis II revealed one of humanity's greatest paradoxes in its sharpest form. This is the paradox between ambition and reality. On one hand, there is a species that can calculate orbits with enough precision to hit a coin in New York with a ball launched from Los Angeles. There is an intelligence that can land a 12-ton capsule traveling at 32 times the speed of sound into the ocean with less than a mile of error. On the other hand, there is a species whose $30 million toilet inside that minivan-sized capsule broke on the first day of the same journey. A species whose communication systems turned into a one-way phone line, whose most basic software crashed, and who discovered that a critical valve meant to keep the crew alive needed to be redesigned. How can we be both so capable and so incompetent? How can we calculate interplanetary orbits to the inch while encountering so many failures in our most basic life support systems? The tragic truth of this question is that what we call the readiness gap is actually a part of human nature. Our ambitions always run a step ahead of our engineering of our capabilities. We dream of reaching for the stars, but we trip over our own shoelaces while doing it. This is a fact that requires humility. It reminds us of how fragile and flawed we are in the face of the universe's vastness. That malfunctioning toilet, that broken communication, that valve needing a redesign, they're all proof of just how thin a thread our massive ambition to reach the stars actually hangs by. And this truth is a sad one that shatters human hubris. Because it shows that no matter how far we go, we take our flaws with us. But hidden within this paradox is also a hopeful, beautiful truth. Because what pushes us forward is not our perfection. What pushes us forward is this very gap, this struggle. It is the effort to fix that broken toilet, the determination to re-establish that communication line, the will to redesign that valve to make it better. The story of humanity is not a series of victories. It is a story of failures, mistakes, and learning from those mistakes. This gap is not a sign of weakness. It is the engine of our progress. You are a part of this paradox too. You have big dreams and small frustrating failures you encounter in daily life. But what defines you is not these failures, but your effort to try again, after them, to fix and to do better. Just like humanity's journey into space. But Artemis II illuminated another, deeper and more personal paradox. This is the paradox between knowledge and cost. On one hand, we are a species that understands the most fundamental laws of the universe, that knows what galactic cosmic rays are, where they come from, how they damage DNA. On the other hand, we are a species that only understands the biological cost of this journey decades later, when it is too late. How can we have the knowledge to send a person 406,771 kilometers away, yet not fully know what this journey does to that person's blood vessels? How can we only see the price of victory in the death statistics of our heroes, in a cold, cruel number like 43%? This is one of the most tragic ironies of modern science. As our knowledge increases, so does our awareness of how dangerous the things we don't know can be. Michael Delp's work shows that the Apollo astronauts may have unknowingly carried the cost of their own victory for the rest of their lives. This is not a sudden death that comes with an explosion. This is a hidden, delayed cost that comes with the slow hardening of arteries, the silent tiring of the heart. And this truth holds a deep sadness, because it means that even our most seemingly innocent discoveries can have invisible, long-term, and fatal consequences. But within this dark picture, there is also a bright light that shows the resilience of the human spirit. Because we now know. The Apollo generation could not have known. They did not have this data, but we do. The 18% radiation surplus brought back by Artemis II told us our models are incomplete. Delp's work showed us where we need to look. This means we're not moving forward blindly. It means we're moving forward with our eyes open, knowing the costs and working to mitigate them. We're no longer just asking, can we go? We are now asking, what is the cost of going? And are we willing to pay that price? And that is a much more mature, much wiser question. You live with this balance in your own life too. You know that every choice you make, every meal you eat, every breath you take has a long-term cost. And living with this knowledge, trying to understand and manage these costs, is part of being an adult, part of being a conscious human being. And finally, there is the most unsettling paradox that Artemis II reminds us of. This is the paradox between the individual and the system. On one hand, there are exceptionally brave astronauts, brilliant engineers, and dedicated managers, individual heroes. On the other hand, There is a slowly drifting yet invisible system that can bring all these well-intentioned people together and drag them towards a disaster. That insidious process Diane Vaughan called the normalization of deviance. How can decisions that all seem right when viewed individually combine to become a fatal mistake? How can a hero like the engineer who warned about the O-rings be powerless against the massive momentum of the system? This is one of the most tragic aspects of the human condition. Sometimes the greatest threat is not a malevolent enemy, but a well-intentioned but blind system that we are all a part of. Now, it shows the helplessness of the individual against the system, how even the brightest mind can be overruled by a corporate habit. The people on Challenger and Columbia were not bad people. They were parts of a system that could not see how a deviation was slowly becoming normalized, and this truth is profoundly saddening, because it implies that no matter how hard we try, we can be defeated by forces beyond our control. But the story does not end here, because we now know this pattern too. Before Challenger, we couldn't put a name to this process. After Columbia, Diane Vaughan gave us this language, this framework. We can now recognize the normalization of deviance. We can understand why the heat shield decision is an alarm bell. This knowledge empowers the individual. We are no longer blind. Yet we no longer have to remain silent. Because when you can name a pattern, you start to see it. And when you see it, you can fight against it. The individual can be a bulwark against the system's drift. You see these patterns in your own life, at your workplace, in your community. You notice how small compromises, ignored standards, slowly become the new normal. And in that moment, you have a choice: to stay silent and be swept away by the current, or to speak up and say, "Stop, this is not right, this is not what we agreed on at the beginning." This knowledge places a responsibility on you, but it also gives you the power to change, ambition and reality, knowledge and cost, the individual and the system. These great paradoxes shown to us by Artemis II prove that space travel is not just about rockets and orbits, as it is also a journey to discover ourselves, our limits, and our potential. But beyond these paradoxes lies an even more fundamental truth about the nature of this journey. Because this journey is not just forwards, but also inward, a journey towards ourselves. This is why the journey of Artemis II, beyond just rockets and orbits, has forced us to confront the most fundamental, most contradictory truths of the human condition. This is not just an analysis of a space mission, but also an attempt to understand one of the deepest paradoxes of our existence, our relationship with time. Because we are a species that simultaneously looks to the future and is chained to the past. Consider this paradox. On one hand, humanity constantly looks to the future, yet we dream of sending humans to Mars, establishing permanent bases on the Moon, and interstellar travel. The entire Artemis program is a product of this forward-looking gaze, this unstoppable desire for progress. On the other hand, the ghosts of the past follow us with every step we take. The echoes of Challenger's 1986 explosion, the traces of Columbia's 2003 tragedy, remind us of the pattern of normalization of deviance. 50 years of data from Apollo show that even those triumphant days can have a long, dark shadow. How can we look so far ahead while being so tightly bound to the cycles of the past? Is this not both a hopeful and a tragic situation? The tragic part is the fact that we cannot fully escape the mistakes of the past. It is saddening to see how stubbornly corporate habits like the normalization of deviance persist through generations. It is like realizing that no matter how fast we run, we can never escape our own shadow. The feeling that history is doomed to repeat itself can give one a sense of helplessness. But there is also a beautiful side to this coin, because this connection to our past is also our greatest strength. We are not starting from scratch. We have the lessons of Challenger. We have the warnings of Columbia. We have an awareness of the biological costs of Apollo that engineers of that era could not have had. The past does not have to be a shackle. It can be a map, a guide, a collection of warning signs left by those who came before us. And when we learn to read this map correctly, we have a chance to break the cycles of the past. You are making this journey in your own life too. You know how your past, the decisions you made, the mistakes you made, and the victories you won have shaped the you of today. And you too, instead of being a prisoner of the past, are trying to build your future more consciously by learning from it. This is one of the most fundamental struggles of being human. And this brings us to another deep paradox, the paradox between story and reality. We are a species that tells stories, that creates myths. The Artemis II mission was a perfect example of our need to tell stories. A perfect landing, a historic achievement, broken records. These are parts of a powerful, just as positive narrative that ignites the human spirit, that inspires us. These stories are necessary. Without them, we cannot find the motivation to take such great risks, to make such great sacrifices. On the other hand, there is the raw, unfiltered, often boring, and sometimes frightening reality. That reality is found not in press conferences, but in the footnotes of engineering reports, in the cold numbers of data tables, 12 millisieverts, 18% deviation, over 100 cracks, a valve that needs to be redesigned. How can these two worlds, the warm light of celebrations and the cold, fluorescent light of inspection reports, coexist? How is it possible that the most important truth is often the least told story? The tragic part of this situation is that the stories we tell can blind us. We can get so caught up in the narrative of victory that we ignore the cracks underneath. The pressure to maintain the success story can lead to the normalization of deviance, to our reframing of disturbing data as acceptable risk. We believe so much in the myth we create that we become deaf to reality's warning signals. But the beautiful part of this paradox is that we have the power to tell a more honest, more complex story. This very video is part of that effort. The act of looking at that inspection report, the will to question that press conference, the determination to tell this second story is, in fact, an act of deep hope. It is the belief that we can choose honesty over comfort, that we can be better than our myths. It is the confidence that the truth, no matter how unsettling, will ultimately make us stronger. You live between these two worlds too. There are the bright moments you share on social media, and then there is your inner reality, more complex, messier, that no one sees. And you know too that real growth begins when you find the courage to face that second story, that raw reality. So, what do you feel when you're confronted with all this information, with these contradictory truths? On one hand, is there that pure admiration and pride for humanity's achievement? Those magnificent images of orbiting the moon, the broken records, the triumph of human intellect and courage. This is a feeling that excites, that makes one look to the future with hope. On the other hand, is there that deep concern and anxiety that arises after learning this data, the cracked heat shield, the flawed radiation models, the fate of the Apollo astronauts? These are also truths that gnaw at one's core, that make one ask, are we really aware of what we're doing? Perhaps you feel both at once, and that is completely normal, because both of these feelings are valid. And perhaps wisdom is the ability to hold both of these feelings at the same time. It is to not lose that childlike wonder that pushes us to go to the stars, while also taking seriously the adult concern that will keep us safe on the way. This is not like hitting both the brake and the gas at the same time. This is driving carefully and consciously, knowing how powerful the car's engine is, but also being aware of how dangerous the road can be. Perhaps the most important lesson Artemis II has taught us is this: real progress is possible not with blind optimism, but with clear-eyed realism, or ambition and reality, knowledge and cost, the individual and the system, past and future, story and reality. All these paradoxes show how complex and multi-layered humanity's journey into space is. We now know that this is not just an engineering problem, it is also a biological, sociological, and philosophical challenge. We now understand that the greatest dangers may not be hidden in rocket engines or computer code, but in our own thought patterns, our corporate habits, and the stories we tell ourselves. But beyond all this analysis, all these contrasts, there seems to be one more question to be answered. Despite all these risks, all these paradoxes, and all these painful lessons, why do we still feel such an irresistible desire to go? There must be something more fundamental, more primitive in the nature of this driving force, beyond all this engineering and politics. And that thing is perhaps something more fundamental, more primitive, beyond all this engineering and politics. This is why now, it is time to descend to the final layer of this philosophical journey. to the place of the most intimate questions. Because all these paradoxes that Artemis II reminded us of leave us with an ultimate question. What do we do with this knowledge? Is it enough just to know the dangers, the risks, and our own flaws, or does this knowledge itself confront us with a deeper responsibility? Because now, we face one of the most unsettling paradoxes, the paradox between knowledge and action. On one hand, we are more knowledgeable than we have ever been in human history. Thanks to Diane Vaughan's work, we have what is essentially a blueprint for how corporate disasters unfold. We know the monster called normalization of deviance by its name. We know how the O-ring erosion on Challenger was ignored for 24 missions. We know how the foam shedding on Columbia became an acceptable risk over 113 missions. On the other hand, there is an organization that, instead of redesigning a heat shield that cracked in over 100 places on Artemis I, changes the orbit to work around it. How can we, while knowing the recipe for a disaster so clearly, appear to be following the steps in the recipe one by one? Is this not history's most brutal irony? The tragic part of this situation is that a mistake made in ignorance is forgivable, but a mistake made with knowledge is a choice. The Apollo engineers did not know the long-term effects of deep space radiation on the cardiovascular system. Their mistake stemmed from a lack of knowledge. But we know the pattern of normalization of deviance, and with this knowledge, we see how dangerously similar the heat shield decision is to this pattern. Therefore, if one day this decision leads to a disaster, it will not be an accident, it will be negligence. This is the weight of knowledge and the deep sadness that comes with inaction. But, within this knowledge, there is also a revolutionary beauty hidden. Because knowing gives us the power to choose. We are the first generation of space exploration that can identify the pattern of disasters in real time, name it, and fight against it. This knowledge is a superpower as much as it is a burden. It gives us the authority to say, stop, we've seen this road before, and we know where it ends. We're no longer victims of fate. We now have the potential to be conscious actors of history. You live this paradox every day too. You know the harms of smoking, the dangers of sugar, the costs of sleep deprivation. This knowledge sometimes feels like a burden when you don't act on it, but it also gives you the power to make a better choice every day. Knowing is the beginning of the struggle. And this brings us to another fundamental paradox about the nature of our ambition, the paradox between the goal and the journey. In space exploration, especially human space exploration, we have always focused on big symbolic goals. Landing a man on the moon, planting a flag on Mars. This is the entire reason for the Artemis program's existence, and these goals are incredibly powerful. They ignite the public's imagination. They persuade politicians to approve multi-billion-dollar budgets. On the other hand, there is the journey itself, the process that is often less glamorous, less headline-grabbing, but often scientifically much richer. Artemis II did not land on the moon, but it took those unique photos of the solar eclipse behind the moon. It observed meteors hitting the lunar surface in real time, and it collected that critical radiation data that exceeded our models by 18%. How can it be that the most valuable thing, the scientific discovery, is often seen as a byproduct on the way to the big goal? This is one of the greatest ironies. The tragic part is that this obsession with the goal can devalue the journey itself. When the question, when will we land on the moon, becomes more important than what are we learning on the way, the pressure to make risky decisions, to hurry, and to put science on the back burner increases. We risk overlooking real discoveries in the pursuit of a symbolic victory. But there is also a beautiful side to this obsession, because that symbolic goal, that big, bold dream, is the engine that makes this whole journey possible. Without the promise, we will land a man on the moon, Congress would never have signed a $4.1 billion check. And without that check, there would be no spacecraft to collect radiation data, no astronauts to photograph the eclipse behind the moon. The goal, even if it is an illusion, is a powerful myth that finances the journey, and this is a pragmatic truth of science. You experience this dynamic in your own life. You set goals like getting a degree, getting a job, buying a house. But when you look back years later, you realize that what truly shaped you was not the moment you reached that goal, but the path you took to reach it, the lessons you learned, and the person you became along the way. And finally, we face the most fundamental tension of our existence, the paradox between time and timelessness. We are a species that lives by urgent, man-made timelines. Landing on the moon by 2028, acting before China. Finding a solution before the ISS is deorbited in 2031. All our programs are shaped under the pressure of these relentless ticking clocks. On the other hand, there is the universe we're trying to explore. Billions of years old galaxies, cosmic rays that have travelled for millions of years. It is timeless, it is patient, it is in no hurry. How can our frantic and our short-term rush coexist with the calm, infinite patience of the universe? The tragic part of this situation is that this clock we impose on ourselves becomes our greatest enemy. This external pressure accelerates the normalization of deviance. It forces us to find temporary solutions instead of fixing cairn to move forward without fully understanding. This pressure, created by our own mortality and impatience, can push us toward the very disaster we're trying to avoid. This race against time often makes us lose time. But there is also a deep and beautiful meaning to this rush, this sense of urgency. Because it is an acceptance that we are mortal. The universe can wait forever, but we cannot. We have only a fleeting moment to seek meaning, to explore, to leave a mark. And this limited time is what gives our lives meaning and value, what gets us out of bed every morning, what pushes us to learn something new, to create something new, is the knowledge that our time is limited. This urgency is not a curse, it is a blessing. It is the fire of action. You live with this tension too, you know that your life is finite. And this knowledge, while sometimes a source of anxiety, is also what makes every moment more precious, every choice more meaningful. The desire you feel to do something while the sands of time are running out is the most fundamental driving force of being human. Knowledge and inaction, goal and journey, time and timelessness. These deep paradoxes show that Artemis II has given us not just a technical report of a space mission, but also a mirror to the human condition. This journey has reminded us of who we are, what we know, what we don't know, and how we live with it all. But at the end of all this internal accounting, all this philosophical questioning, one question remains. What is the ultimate purpose of this journey? Is it just about understanding ourselves better? Or do all these risks, these costs, and these efforts serve something greater than ourselves? Because perhaps the deepest layer of this story lies in the fact that this journey is not just about us. Perhaps the real issue is not what we find in this universe, but what we leave behind in this universe. And therefore, at the deepest layer of this journey, perhaps the real issue is not what we find in this universe, but what we leave behind in this universe. This question takes us beyond engineering and politics to one of the most fundamental contradictions of our existence. This is the paradox between loneliness and connection. On one hand, space travel is the most absolute act of loneliness in human history. 4 people, hundreds of thousands of kilometers from Earth, inside a capsule the size of a minivan. If something goes wrong, help is millions of kilometers and minutes of radio delay away. This is a situation lonelier than being on a raft in the middle of the ocean. It is a confrontation with one of our most basic fears, absolute isolation. On the other hand, this absolute act of loneliness has an incredibly unifying power that brings together millions of people on our planet. While those 4 astronauts are alone, we all watch them together. Their journey becomes our journey. Their victory is our victory. Beyond national borders, political differences, and cultural divisions, we look at that small capsule and say, we are there. How can the most isolating physical act turn into the most unifying spiritual experience? The tragic part of this situation is the brutal reality of that physical loneliness. Those astronauts are truly on their own. No matter how much we love them, no matter how much we support them, we cannot reach them in that void. This painfully reminds us of the physical limitations of human connection. But the beautiful truth within this paradox is that this physical separation creates a deeper emotional and spiritual connection. Those astronauts are there on our behalf. They are the ambassadors of humanity's curiosity, courage, and imagination. And this shared representation connects us to each other in a way that nothing has ever connected us before. You are a part of this paradox too. Sometimes you feel lonely in a crowd, but you also know that you can instantly form a bond with a stranger with whom you share a song, a movie, just or a dream. We are beings who are lonely but also deeply connected. And space travel is the most magnificent expression of this fundamental truth. And this brings us to another deep paradox about the nature of our power, the paradox between creation and destruction. On one hand, there is the incredible creative power of humanity. We build a rocket, the SLS, powerful enough to escape Earth's gravity from scratch. We design a heat shield to protect a vehicle entering the atmosphere at Mach 32, at a cost of approximately $4.1 billion. We create these incredible machines that are monuments to human intelligence and collaboration. This is an act of pure creation. On the other hand, there is the fact of how destructive this creation process itself can be. Starship test flights end in spectacular explosions, programs are halted due to anomalies, the story. And most tragically, as in the case of Challenger and Columbia, these machines we create, due to flaws we also created, can destroy themselves, taking their creators with them. How can our act of creation also contain the seeds of destruction? The tragic part of this situation is the fact that no creation is perfect, and every technology, no matter how glorious, carries a potential for failure. Our power to create is also our power to destroy, and the balance between these two hangs by a thread. The momentary failure of an O-ring can destroy a decade of work and 7 lives. This is a sad truth that reminds us of the fragility of our creativity and how great our responsibility is. But there is also a hopeful beauty in this paradox, because destruction is also the beginning of recreation. After every failed Starship test, SpaceX learns from the wreckage and builds a better, stronger rocket. After the Challenger disaster, NASA recreated its safety processes. After Columbia, it confronted its organizational culture. Destruction, though painful, is also the catalyst for growth, evolution, and a wiser creativity. You experience this in your life too. Sometimes your greatest creative breakthroughs come after your greatest failures, your most painful losses, because rising from the ashes is not just a myth, but also one of the most fundamental dynamics of the universe and the human spirit. And finally, at the end of all this philosophical journey, we are left with perhaps the most personal paradox, the paradox between the search for meaning and silence. Yet we are a species that seeks meaning, that asks why. Why do we go to space? Why do we take these risks? Why do we spend billions of dollars? We shout these questions into the great dark silence of the universe. On the other hand, there is the universe itself. It does not answer us. It seems indifferent to our existence. It offers neither a purpose nor whispers a meaning. It just is. Cold, indifferent, and silent. How can the most meaning-seeking beings in the universe live in what is seemingly the most meaningless place? This is the most fundamental tension of existence. The tragic part of this situation is the possibility that the great external meaning we seek may not exist at all. It is the thought that all our efforts, all our struggles, all our discoveries might be meaningless, screams echoing in an indifferent universe. This is a chilling, just, sad possibility. But in this silence, the deepest and most beautiful truth is hidden, because, since the universe does not give us meaning, we are free to create our own. Meaning is not something discovered. Meaning is something built. Meaning is in the very act of asking that question. Meaning is in the courage to embark on that journey. Meaning is in the connections we form in the face of those difficulties. The silence of the universe is not a void. It is a canvas, and we fill that canvas with our own dreams, our own questions, our own art, and our own science. This is our greatest freedom. You're searching for the meaning of your own life too, and you know too that that meaning will not descend from the heavens like a revelation. You are building that meaning yourself, every day, with the choices you make, the people you love, the things you're passionate about. You are the artist of your own existence. We now know that we live in a constant tension between our ambitions and our realities, our knowledge and our costs, our past and our future. We now know that no matter how brilliant we are as individuals, we are vulnerable to the blindness of systems. We now understand that we will not find meaning somewhere out there. We will create it inside, with our own actions and our connections. The 10-day journey of Artemis II showed us not only the dark side of the moon, but also this complex, contradictory, and ultimately beautiful face of our own existence. And at the end of this long journey, after all the failures, victories, data, and doubts, one simple question remains. With this knowledge, with this awareness, with this new maturity, what will we do now? In this video, we saw how fragile we are on our journey to the limits of the universe. But there's something I didn't tell you. What if this journey, this reality, is not what we think it is? What if this entire universe, all the stars, all the galaxies, and even you, are part of a complex computer simulation designed by a higher intelligence? On our next journey, we will explore the evidence and contradictions of the simulation hypothesis. Are you ready?